Hi, I am Sreedhara R, Assistant Professor of Physics, Government First Grade College, Foruman, ತುಮಕೂರು. ಇವತ್ತು ನಾನು ಜ್ಞಾನನಿಧಿ ಯೂಟ್ಯೂಬ್ ಚಾನಲ್ಗಾಗಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಪೊಲರೈಸೇಷನ್ ಆ್ಯಂಡ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ವೆಕ್ಟರ್ ಎನ್ನುವ ವಿಷಯದ ಬಗ್ಗೆ ವಿಡಿಯೋ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಈ ಟಾಪಿಕ್ ಬಂದ್ಬಿಟ್ಟು ತುಮಕೂರು ವಿಶ್ವವಿದ್ಯಾನಿಲಯದ ಪ್ರಥಮ BSc ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಮೊದಲನೇ ಯೂನಿಟ್ನಲ್ಲಿ ಇದೆ. ಇದು ಲಾಸ್ಟ್ ಟಾಪಿಕ್ ಆಫ್ ದ ಫಸ್ಟ್ ಯೂನಿಟ್. So now I am going to explain in detail about the electric polarization. So electric polarization it is also simply called as just a polarization. It is a vector field. It is a vector field. We can express this as a electric dipole moment per unit volume or density of the electric dipole moment. So in the electric dipole moment, we can find the two types. One is the permanent electric dipole moment and other is the induced electric dipole moment. So permanent electric dipole moment means in a dielectric material we can find the two types of molecules. One is the polar molecule and other is the non-polar molecules. In a polar molecule, the two charges, positive charge and the negative charge, that means the proton and the electron, their center of gravity is separated by a small distance. So therefore those two charged particle, proton and the electron, form electric dipole. So the molecules or the dielectric material having the molecules have its own electric dipole moment, and those electric dipole, they are not oriented in a particular way, but the orientation of the electric dipole is random. So therefore if you find the net electric dipole moment in such cases, the electric dipole moment will be the zero. So because they are randomly arranged, the direction is different in all the direction, then if you take the sum of those electric dipole moment, the net electric dipole moment will be the zero. The dielectric material of such polar molecules, if you placed in an external electric field, these randomly arranged dipoles will come into one particular direction, which are along the direction of an electric field. Therefore there will be a net electric dipole moment due to this electric field. We know that the dielectric materials we are used in a capacitor, in the space between the two parallel plate capacitor. So therefore there is electric field. Due to that electric field, these polar molecules are arranged in a manner due to the electric field. Therefore there will be a net electric dipole moment. Then the process, the phenomena, is called polarization. Due to that polarization, there will be electric dipole moment. The electric dipole moment per unit volume of that dielectric material is the electric polarization. Now I said the dielectric materials may have the polar molecules and the non-polar molecules. In the case of dielectric materials with non-polar molecules, the center of gravity of positive charge, I am explaining for the non-polar molecules. For a non-polar molecules, the center of gravity of the positive charge is exactly coincide with the center of gravity of the negative charge. Therefore, there is no dipole in a non-polar molecules. So therefore, there is no electric dipole moment. In such dielectric material which are placed in the electric field, the charge centers of the non-polar molecules becomes displaced. So in the absence of an electric field, the both positive and negative charges, the center of gravity of both positive and negative charges will coincide. When the electric field is applied, those are displaced. The positive charge and negative charges are displaced by a small distance or a finite distance. So then the molecules are said to be polarized by the external field and are called induced, because due to the electric field they becomes a dipole. So therefore they are called induced dipoles. Thus the molecules acquire the induced electric dipole moment, and this is in the direction of the field. So we can show that in the pictorially, in the figure we can show as, so you can see, in the absence of an electric field, both positive charge and negative charge of the center of gravity will coincide, will be the same. So therefore when the field is applied, they are displaced. This is the center of gravity of the negative charge, which is exactly center, and this is at the center. There is a small distance. So that distance, due to that small distance, electric dipole will be formed. I said already, in the case of dielectric materials with the polar molecules, in the beginning only the center of gravity of the positive and the negative charges are separated, and here they are randomly arranged. You can see they are randomly arranged in the absence of an electric field, and the dielectric material is placed in the space where the electric field is present between the two parallel plates. Then the polar molecules has the electric dipole, hence they are called electric dipole moments. In the absence of an external electric field, the individual dipoles are oriented randomly. So therefore the net dipole moment in dielectrics is zero. When the electric field is applied, the force on the dipole gives, so because here you can see they are randomly arranged, so when the force is applied, the force is different at the different at the points, so therefore there will be a torque. So there, and those dipoles will rotate and will move, or will be arranged in this manner, so in the direction of electric field. So due to this effect, all the dipoles orient in one direction along the electric field. Hence, the dipole moment produced in the dielectric materials. Thus, the phenomena of orientation of the induced dipoles are the permanent dipoles in an external electric field. So that to set the axis of the dipoles along the field, along the applied electric field, the phenomena is called as electric polarization. This is electric polarization, the process. This is the process. When you want to define this, this is electric dipole moment per unit volume, or density of electric dipole moment. And we know that this magnitude of the dipole moment, so usually we are represent the dipole moment by a small letter p, and it is a vector quantity. The magnitude of that dipole moment is found to be directly proportional to the magnitude of the applied electric field. So thus we can write the P is directly proportional to E, and P is equal to proportionality constant alpha, and this alpha we are called the molecular capability of the dielectric. So thus the electric polarization want to be defined. So electric polarization we usually represent the capital letter P, and is defined as the product of the dipole moment and the number of molecules per unit volume. So small p into number of molecules. If you call the number of molecules as n, so n into p. So then p is equal to np. So capital P is the polarized electric polarization, small p is the electric dipole moment, and n is the number of molecules in unit volume. Then P is equal to Np is the polarization, electric polarization in the dielectric material. So thus the polarization P is defined as the dipole moment per unit volume. It has the same direction of the P and E. Small p is the dipole moment and E is the electric field. So therefore the electric polarization, electric dipole moment, and the electric field, these three are in the same direction. So now we'll go to the next topic, displacement vector. So this displacement, the electric displacement vector, is also a vector field in the dielectric medium. It is also a vector field in a dielectric medium which is directly proportional to the electric field. It purely depends on the electric field in a dielectric materials where the dielectric material is placed. So you can think of that this dielectric material we have to be used in capacitors, parallel plate capacitors between the space of two parallel plates. So therefore, displacement vector we use the letter capital D, and this displacement vector D is directly proportional to E, and therefore D is equal to epsilon naught proportionality constant epsilon naught epsilon R into E. So suppose in a parallel plate capacitor with a dielectric medium, parallel plate capacitor is anta andukondre. So and with a dielectric medium, so we are placed the dielectric material. In such cases, if the Q is the charge given to the plates, and there will be a Q dash charges will be induced on the boundary of the dielectric material. ನಾವು Q ಚಾರ್ಜ್ನ ನಾವು ಪ್ಲೇಟಿಗೆ ನಾವು ಕೊಟ್ಟರೆ Q dash charge dielectric material border ಇರುತ್ತಲ್ಲ boundary of the dielectric material where the Q dash amount of the charges will be induced in the dielectric materials. So therefore we can write the equation for this case Q divided by A. Q is the charge on the plate divided by A is the area of the plates, and epsilon naught E is equal to Q dash divided by A. Q dash is the induced charges in the dielectric material. A is the area of the dielectric material. So both are the same because we are introduced the dielectric material in between the parallel plates. So therefore the dielectric material is also having the same length and breadth, same dimension. So therefore we can write this expression as capital D is equal to epsilon naught E plus P. So where D is equal to Q divided by A and P is equal to Q dash divided by A. So therefore this D is called the electric displacement vector, or simply we call it the electric displacement, and this capital P is called the electric polarization. And you know that this E is the electric field between the parallel plates and A is the area of the plates. Since and we know that E and P are the vectors, electric field and polarization both are the vectors and they are in the same direction. Therefore D must be a vector, and the vector D is also in the direction of the electric field and the electric polarization. So this is about the displacement vector. So thank you.